title of the project was to develop vanadium microalloyed steel for thick normalized plate, basically above 50 mm thickness. So we are working with JSPL for this project. So our target is to achieve is 460 in grade in normalized condition. These are the typical range of the chemistries as per EN 10028, and the mechanical property requirement is here. So the challenges is the achieving mechanical properties in this range, especially yield strength in greater than 50 mm thickness in normalized plate is very challenging in industrial production. So, and in this grade we have vanadium up to 0.2% maximum. So we are trying to add vanadium and getting these property in the mechanical property in the normalized condition. Also there are other alloying elements which we will be trying further. So after this requirement, we have studied literature. These are the summary of the literature. David also suggested some literature. It was very beneficial. And then so with increasing the nitrogen content, most of the literature suggests that vanadium nitride precipitation stability increases, and during soaking at 900 degree, some papers suggest that 30% precipitate will not dissolve, and the existing precipitate during normalizing to temperature leads to refinement. They can act as a depletion site and also restrict the austenite grain size. After normalization, people are suggesting that only 50% of the total vanadium weight percent is precipitated, others are in solid solution. So this is also a concern. So, and for significant gain refinement during normalizing, some papers suggest that we need to have at least 100 ppm nitrogen as vanadium nitride. So highest strength and toughness combination by the study of Sage et al. In Nature Technology paper, they suggested that at least we should not allow the aluminum content too high, at less than we should maintain 0.1%, and nitrogen should be there. And so Navium apparently does not contribute to the strength in the normalized steel plate as per the literatures, and high carbon manganese is required to achieve 460 MPa strength. And so we concluded that high vanadium and nitrogen along with low aluminum would be the very effective way for strengthening in the normalized plate. And some paper also suggests that titanium, even with 0.15 addition, we can decrease the strength because they will take away the nitrogen from the vanadium. So the scope of research in this normalized plate is there is a competing effect of grain refinement and precipitate refinement, because they will dissolve and then deprecipitate. So we need to optimize the vanadium nitrogen normalizing temperature also, so that we can get either strength and toughness combination. So higher normalizing temperature is needed for dissolution, but at the same time austenite grain will course. High carbon and manganese is required for achieving the highest strength. So this was the scope of research. So with this study, we made two different steel, with one with low nitrogen, another with high nitrogen. Same chemistry we maintained with vanadium 0.15%, and we kept aluminum in lower side. In one case we achieved, so on case we achieved 80 ppm, another case we achieved 150 ppm. So these are the thermochemical study we have done, and here we can see at higher nitrogen content, vanadium nitride starts at around 1100 degree centigrade temperature. As we decrease the vanadium level to 0.15 to 1.1, so the vanadium nitride crystal temperature is also decreased. And with higher aluminum and nitrogen, aluminum nitride can also precipitate at around 1050 degree centigrade temperature. So these are the temperature profile we measured for a thick 50 mm plate, and the cooling rate around 12 degree and 20 degree centigrade in the respectively core and surface. So these are the two chemistries we produced, one with 90 ppm nitrogen, another with 150 ppm nitrogen. with same level of vanadium, same level of carbon manganese, and etc. With one with aluminum 80 ppm, another with 150 ppm. So we actually hot forged this steel because in our institute, hot rolling temperature will decrease very fast. Here with the laboratory steel, so we try to simulate the hot rolling in hot forging, and we then normalize the steel at 900 degrees centigrade and cooling at different rate, 5 degrees centigrade, 10 degrees centigrade, 20 degrees centigrade. So these isometry results suggest that AR1 and AR3 is around 615 and 730 for all the steel similar AR1 and AR2 got, and for all the cooling rate. Now in the DSC result, we observed that during heating, there is only one change in the calorimetric value, energy 741. Here is the phase transformation. But in case of cooling, we got actually three different harms in case of cooling. This is the derivative of DSC, and this is where we are expecting vanadium nitride precipitation, because in this steel only this can precipitate. There are no other element for to precipitate, or any phase transformation is not there. So this may be vanadium carbonate and this may be vanadium carbide. And from the diatometry result, we can see that the 611 is the AR1 temperature. This is the range. So this is due to the phase transformation, and these two are due to the vanadium carbide, carbonitride, and vanadium carbide precipitation. For both the steel, we observe similar type of temperature, 877 and 874, here 740 and 750. So the optical microstructure of asphalt and the cooling rate at 10 degree and 20 degrees centigrade, we observe that ferrite pearlite structure, almost recrystallized ferrite and pearlite structure, and for both the cases, and 90 nitrogen. Here apparently it looks like a little bit refinement takes place, but when we measure the grain size and the pearlite fraction from the SEM and optical microscopy, we found that the grain size range of ferrite grain size is 90 and AF we are getting 12 micrometer, and in case of 150 we are getting 9 micrometer. And pearlite fraction little bit higher in case of asphalt sample, but when we are cooling at 10 degree and 20 degree, it is decreased in both the cases. In both the cases, 90N and 150N nitrogen, we are getting higher pearlite in asphalt condition. As we are normalizing it, so the pearlite fraction also decreases, and obviously the grain size also decreases. In 20 degree, we are getting at least 6 micrometer grain size. So, but this is the hardness value. You can see that in case of 90 and asphalt, we are getting highest hardness value to 15 MP, and here we are getting as we are normalizing the steel, at least 30 HB hardness is dropping in both the cases almost. So now the EBS analysis we have carried out here, also random texture we have observed, and some low angle boundary we observed in case of asphalt sample, whereas 10 degree and 20 degree centigrade we did not observe that. So we have plotted the grain boundary misorientation angle versus frequency. For asphalt sample, little bit low angle grain boundary observed in both the cases, but in case of 19 it is comparatively higher. But in all other cases, similar type of angle grain boundary observed from the microstructure study. So we could do only two tensile testing in the two different chemistry, 90N and 150N. In the asphalt condition only, we could not do the normalized condition. Sample is under preparation. So here we observe 522 yield strength and 513 yield strength in case of 90 nitrogen and 150 nitrogen with UTS in this range, and elongation around 20%, and this of the hardness value. So we were expecting that with increasing the nitrogen, concentration, the yield strength will increase significantly, but somehow in case of this asphalt steel, we are not getting that. So we have also studied the micro hardness from both ferrite and pearlite region. Here also, in case of 90 nitrogen asphalt condition, we are getting 200 hardness in ferrite and 295 in pearlite, whereas in case of 150 nitrogen, we are getting lower value in ferrite and pearlite both. So, and also in normalizing, it is expected that the hardness will decrease both in ferrite and pearlite region. Now, the TEM micrograph from 90 nitrogen, we have observed from extraction replica technique we are using here, and we have observed that some cuboidal and irregular shape precipitate. Sometimes it is very high in concentration in few places. In the pearlite region also we have observed some precipitation. The size range is 2 to 17 nanometer. In the dark field images also we can observe some precipitate are coarser. Here also it is, you can see that some precipitate are coarser and some are very fine. Okay. So in case of 150 nitrogen, actually precipitation concentration a little bit decreased. There are some fine precipitate inside, but some precipitate is around 80 nanometer and coarse and spherical precipitate. Here we did not observe. And also some precipitate clustering we observed here in the extraction replica. Okay, inside the pearlite also some precipitate we observed. But we could not confirm if EDS or EDS was under maintenance. So in the next presentation, we probably will be doing a good TM study and quantify all the precipitate, because here we only could do some 3-4 sample. We wanted to do more sample and then count the precipitate and their size fraction, volume fraction, and correlate with the strength. So the summary of the research is that we could achieve around above 500 MPa in hot forge condition with this chemistry, and we are expecting that we will be achieving 450 MPa in normalized condition. But above 460, I think we will not be able to achieve this time. But we will be analyzing the data and TEM study, and after that we will be deciding the further course of action. So there may be, from the study it shows that there may be no strengthening effect of increasing nitrogen content in this particular vanadium due to maybe the coarse vanadium nitrate precipitation as the precipitation taking place at very high temperature. Ferrite pearlite microstructure is observed in both the exposure normalized condition microstructure and microstructure banding is also observed at 10 degrees centigrade per minute. Cooling rate, especially 20 degree banding little bit reduced. Bulk hardness of microdata shows a decrease in hardness in normalized steel is expected. Apparently, the 0.15 B90 and steel shows the more concentration of cuboidal and irregular vanadium precipitate, but we need to see more replica, then we will be able to confirm along with the fine vanadium precipitate compared to 150 M. Though it is not expected from the literature, but we observe only that. Pearlite region is also having some precipitation in both the steels. Some clustering of precipitate is also observed, which may be due to the high temperature precipitation in this high vanadium high nitrogen steel. So our future plan is we will reduce the vanadium concentration a little bit, 0.1 vanadium level, so that the temperature of precipitation a little bit less. It is expected that 1000 degree will be the temperature precipitation, and also we will vary the we will see at this steel also at 875 degree centigrade temperature. Maybe there will be effect of grain refinement or state grain refinement, and also some precipitate will be within there. So then we will check if there is any effect of high grain refinement in class B precipitation, then vanadium precipitation strengthening on the strength. And we will do extensive TM study, and also water point sample from here we will be studying to get the idea of what type of precipitation is there at that time, and during cooling, what type of precipitate, what is the amount of precipitate we are observing, and then contribution of different strengthening will be calculating, and the industrial partner JSPL wants to have somewhat ductility curve for their for this high vanadium nitrogen steel, so that they can easily cast. So in year-wise deliverable, we have achieved this detailed literature review. Also, the melting rolling tiles review result, microstructure property. So we will be submitting this abstract on in a conference, Indian conference next time, and 2024 plate symposium as suggested by David. And then some detailed characterization is also carried out, and some are pending. And all the vanadium other vanadium containing grades like low vanadium, high nitrogen, this type of grade with nickel we will be studying in the next 6 months, and we will be presenting them. Okay, thank you very much.
Okay, thanks very much for that presentation. I think we made some good progress there. Are there any questions or comments on this presentation?
Yes, I have one comment. Yeah, if I'm Debala, if I can go ahead.
Yes, please do, Debala. Yeah.
Yeah. Yes, Dr. Patra. So nice presentation. So as we were discussing that since you were normalizing at 900, so it's very important. Dr. Dev and other experts may also comment. It's very important whether the pre-existing precipitates are dissolving or not. That the ideal situation would be if the pre-existing hot forged condition, whatever precipitates are there, if we can dissolve them and then fresh precipitate can form, then strength is expected to go up. Otherwise, if they are not dissolving, then that will control the grain size, but strength may not be that high. But toughness you are testing, by the way?
Yes, we will be testing, but till now it is not done.
Okay, so your grain size is quite fine, so toughness is expected to be high, but to achieve strength, your normalizing temperature should be such that everything should go in solution. This is my comment. Thank you.
Yes, sir.
Yeah, if I could just comment on that, Deble, I think what we'll probably achieve here is that at the normalizing temperature of 900, we'll get a partial dissolution of the vanadium. So we'll get some vanadium nitride, which will give us grain refinement, and we will dissolve some of the vanadium, which should give us precipitation strengthening. So it's a combination of the two. If I could ask a question, you haven't got any tensile test results in the normalized condition yet. Is that something we'll see later?
Yes, definitely. Actually, the samples are under preparation. I think within a day or two we'll be getting this result.
Okay.
This normalized condition result. But from the data of Asperge and the grain size and all, we are expecting around 450 from the hardness also. We are getting hardness values like 185 in this way.
The other comment was you don't notice any strengthening effect from the higher nitrogen content in the as forged condition, which is a little unusual, I'd say. Would you like to? I know you made some comments about the precipitates. Would you like to expand on that? Why we're not getting any boost in strength at the high nitrogen?
Yes, that is also surprising to me, because in all the literature it is suggesting that this 10 ppm addition of even 10 ppm addition of nitrogen will increase 7-10 MPa yield strength, but even with the 68 nitrogen we are not getting any increase in the strength. So what happened actually, what we found that in case of 0.15 vanadium and 90N, this as forged sample, little bit low angle boundary is there. Maybe the sample is rolled little bit lower temperature. Maybe that also contribute little bit. But the thing is that that is not very significant. The precipitation is also, concentration is also higher. Whatever sample we have seen 1, 2, there we observe that higher precipitation density. in case of 0.15B and 90N, which is not expected. So I will definitely investigate in details. So that is why I want to make another steel with zero point 0.1 vanadium and vary the nitrogen also. Then we'll observe, and also the TEM study, even checking twice the samples. We have made 3 10 cell samples, and there we got this result consistently, not variation in the result. We are getting in between 520 to 525 in this range only. We are getting the yield strength wise UPS. Okay, so but we will be looking into this in detail.
Sudipta, Dr. Singh here. Just I missed actually. The forging is done from which size to which size it was reduced? Have you mentioned it?
Yes, 100 to 20, from 100 mm to 20 mm. 100
Okay.
mm was our initial thickness and 20.
Okay, fine. Good.
Dave, just on your question, yes, it was surprising for us as well that we were not seeing any strength improvement in the higher nitrogen one, despite having a lower grain size in the higher nitrogen. The average grain size was about 3 microns lower than that, but still we were not noticing any strength improvement. So possibly it is something to do with the precipitation, and as very rightly pointed out by Debalai as well, it may have something to do with the amount of dissolution of vanadium nitrides or co-precipitation or heterogeneous precipitation on the existing interfaces somewhere during that. So we need to do a detailed study on that. That is still deep.
Yeah. Okay. I'll be interested to hear what your conclusions are in the next meeting. Okay. Well, in the interest of time, I think we'd better move on to the next presentation. So if you could stop sharing your screen, please. And the next presentation is from our colleagues in Swerim in Sweden, and I think Marcus is going to be making this presentation. Is that correct?
Yes, thank you very much.
Okay, thank you.
I'll try to share my screen. Oh, it says I cannot share while somebody else is sharing. Could you please?
I think, yeah, right.
Thanks. Thank you very much.
Okay, just as a reminder for everyone, this project's been going a couple of years now, and we're moving on to a different